Okay, we are continuing on here, chapter 16, second to last chapter, almost done. So last time we got into, after the quiz there, talk about acids and bases. And remember, sort of your basic sort of definitions of acid and bases is an acid is really something that can produce H plus ions in solution, while base is sort of anything that can really produce hydroxide ions in solution. And it's the ability to produce these guys sort of free by themselves in solution, which makes them either an acid or a base. Also really important in sort of acid-base chemistry is the idea that you will see H3O plus, which is the hydronium ion, and H plus, which is the hydrogen ion, sort of used interchangeably. And again, they're used interchangeably in both the formulas, also reactions, sometimes they're used as well. So again, anywhere, and I think I might have mentioned this last time, I personally lean to just writing H plus. So anywhere I sort of write H plus, you really can't swap it out for H3O plus, is sort of the same deal. Now, sort of an early definition is these guys here that we can produce OH minus or H plus. A more sort of general definition of acid and bases, which a lot of people sort of think about when they are discussing acid and bases, are the Bronsted-Lowry definition. And the Bronsted-Lowry definition, an acid is a proton donor. So it is something that will give away an H plus, while a base is a proton acceptor. And that obviously is something that will accept the H plus in a reaction. So the result of that is that it will, we have sort of a generic reaction here. If this is an acid and water here acting as a base, it is the acid that will accept the H plus over there to water. The result of that is an A minus, not that, let's try that again, A minus plus some H3O plus. And what it creates is acid conjugate base pairs, and acid conjugate base pairs on the opposite side here. This would be the guy that is related to the acid. It would be known as the conjugate base. While the base, which is our water here, would be related to the guy on the other side, which is known as the conjugate acid. So it creates these sort of partners that we see, and they are only a difference of the one H plus that has been transferred. So it is just this one H plus that is the difference between those two guys. So the acid, because it does donate it, will have one less H plus when it gets onto the other side there because it gave it away. While the conjugate acid on the right-hand side there that came from the base will have one more H plus because it actually will accept, obviously, the H plus in this case. It is also important to remember, as we talked about, that it is not just a hydrogen that's being transferred. There is the plus part of it. It does affect the overall charge of what you get on the right-hand side of your conjugate acid and conjugate base pairs. Again, if you lose a positive charge, you become one more negative. And if you obviously gain a positive charge, you become one more positive. So you do need to make sure that you adjust the actual charges on the conjugate acid and base pairs, or the conjugate acid and conjugate bases as you do that. If it is more than one H plus difference, they are not related to each other. And it's really based on this idea that it is just one proton that always gets transferred basically at a time. Any questions on that there? We also talked a little bit about at the end there, I think, the strength of acids and bases. So obviously, if we have a strong acid, it is a strong electrolyte, which means it will 100% break apart into ions. So again, hydrochloric acid here is a strong acid. it will, when it is in solution, 100% break apart into H plus and Cl minus. Again, floating around in that solution is everybody on the right-hand side here. You have no HCl units still together when it's in solution. And really, this is why it is a strong acid, because pretty much when it goes for a swim, you produce a bunch of free H pluses, floating around in there really, really quickly. And that obviously will make the solution more acidic because of that. Now, we talked about some strong acids. Again, hydrochloric acid is a strong acid. Sulfuric acid is a strong acid. Perchloric acid, also a strong acid. Hydrobromic acid is a strong acid. Hydroiodic acid and nitric acid. So this is sort of the big list, if you will, of strong acids. And as I mentioned before, if you sort of remember these acids, especially if you're going to continue on taking more chemistry classes, if you understand these acids are strong acids, you can make a pretty safe assumption that if it's not on that list, it's probably going to be more on the weak side or a weak acid in that particular case. Now, a weak acid is also a weak electrolyte, and much like we talked about when we talked about weak electrolytes, they mainly stay together. But they are able to produce a little bit of ions. So HF is, again, an example of a weak acid. When it breaks apart in solution, it does break apart into H plus and F minus. The difference, again, between HCl and HF is we're only going to get really a few of these guys in solution. It is mainly going to still stay together. So if we sort of look at our beaker there, in a solution of HF, you mainly have HF actually still together, and you do produce a little bit of H plus and F minus. So because it's able to produce a little bit of those HFs, those H pluses, it is still considered an acid, but it will not produce anywhere near what you will see, for example, in hydrochloric acid, which pretty much 100% just breaks apart and produces a lot of H plus really, really quickly. We also can recognize a lot of times weak acids as weak electrolytes. Again, it's a reversible reaction, which means, some of those products will come back the other way to our HF that is together. So HF is a very common weak acid. Acetic acid is another very common weak acid. That's sometimes written C2H4O2. So that's another common one. Nitrous acid, HNO2, is a weak acid, and things like HCN and so forth. So like I said, most likely easier just to kind of get a handle on which ones are strong, and then they probably very safely assume outside of those guys will probably be weak acids. Any questions on any of those things? Now, in terms of bases, also there's strong bases, obviously, and weak bases. And in terms of strong bases, for the most part, the strong bases will have hydroxide in the formula, and usually be members of group 1 and 2 on the periodic table. So things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and so forth. So really, if you look sort of at group 1 and group 2 on the periodic table, right around really lithium, I guess, I go lithium down to like potassium, hang a right, go up just a little bit and down. Any of those guys that have hydroxide in it probably are going to be strong bases. And again, as we talked about the names of those guys, alkali metals and alkaline earth metals, the word alkaline, again, is refers to being basic. So that's where, again, a lot of our strong bases come from. Much like acids, strong bases will 100% break apart, which is why they are considered strong bases. So something like sodium hydroxide, when it goes for a swim there, is going to 100% produce the sodium and hydroxide ions. You'll have none of the unit here still together. It will all completely have broken apart. So what that means is in that beaker, once again, here you produce a lot of OH minus really, really quickly. And that is going to make it a basic solution, most likely. And that is why it's a strong base. Obviously, there would be some sodium ions floating around with it. Now, there are some weak bases that don't have hydroxide in them. And most popular one, if there's a popularity contest, is ammonia is a weak base. And when ammonia reacts or really goes into water, since it's usually a gas, when it goes into water in its aqueous sort of form, it acts as a base and actually will accept the H plus from water, which means in this particular case, water is going to act as an acid. And the result of that is you will form NH4 plus and OH minus. This is why if you ever later on in chemistry life here, I think at this school, they oftentimes will ask you to add ammonia to in an experiment, you would reach for the bottle of NH4OH because that is basically ammonia in the aqueous form. It's ammonium hydroxide. So because of this, it is a weak base. It will form a few of these guys, but we will mainly sort of have this guy in solution. So once again, since it's able to still form some hydroxide here, it is considered a base. Once again, nowhere near as strong as something like sodium hydroxide, which, like I said, pretty much just needs to go into the beaker or whatever it may be, and it will produce a lot of hydroxide really, really quickly. Any questions on any of that stuff there? Okay. So there is also an important sort of relationship between acids and bases and their conjugate pairs, and that is sort of an opposite relationship. And if you have a sort of conjugate partner that came from a strong acid or even a strong base, this partner will be relatively weak. And so, for example, if we looked at just hydrochloric acid, we'll throw it in water here. Once again, it's going to donate its H plus over, going to make H3O plus and Cl minus. So this would be our acid. The conjugate base here would be our Cl minus. And Cl minus, it would be considered a relatively weak conjugate base. And what it means really, and if you take 1B, you'll learn all about this, but basically what it means is the Cl minus won't continue to react with water. It's kind of a neutral salt is sort of considered. It will pretty much keep the pH around 7, and it really won't affect anything. And that's different than if you actually took, for example, HF, or weak acid. And again, we'll use our water here. And again, donating the H plus over, going to make our H3O plus and some F minus. Once again, the relationship here is this is our acid. That would be our conjugate base. What happens when you produce something like F minus in solution, because it comes from a weak acid, it is going to be a relatively strong conjugate base. And let me just say, it's going to be strong in the sense of weak, not as strong as like sodium hydroxide or anything like that. But what it will do in solution, because there's a lot of water basically floating around in that solution, the F minus will decide to continue to react with water. And what it does when it reacts with water is it actually will act as a base, like as a conjugate base. So it will act as a base, which means it will also accept an H plus. And the result of that is it will actually make some more hydrofluoric acid, but it will actually make some hydroxide. And if you had a solution of something like sodium fluoride, it actually would be a basic solution because will continue to react with water and go through this. This is what is sometimes referred to as a hydrolysis reaction, which means it reacts with water. And there's certain salts, right? So when we react an acid and a base together, we produce a salt, which is an ionic compound. And there's certain salts that are produced as a result of those reactions, and especially the salts that come from a weak acid or weak base, they will tend to continue to react with water and actually affect the pH of the solution. In this case, it would actually make a solution a little bit more basic if you had a solution of F minus in this particular case. So there's sort of an opposite relationship. Anything that comes from a weak acid or weak base is going to be relatively strong, which means it has the potential to react with water and kind of continue to sort of affect the pH. Anything that comes from a strong acid or strong base is going to be relatively weak, which means it really won't react with water. It's just sort of neutral. It's just going to kind of hang out there, not do much in terms of the pH of the solution. There's a whole chapter in Chem 1B on those reactions. Any questions on that there? So there's our strong acid list again. Again, also some terminology in terms of acids is based on how many hydrogens that it can give away. So something like HCl, which has only one hydrogen to give away, it is what is referred to as being a monoprotic acid. Obviously, mono meaning one, protic meaning proton that it could give away. Something like sulfuric acid actually has 2 protons that it could give away. And this is what is sometimes referred to as being diprotic acid. And there's even some like phosphoric acid, which can give away a total of 3 hydrogens, really to balance out the charge there of phosphate. And this is what is sometimes referred to as being triprotic. So different acids can give away different amounts of H's, but it's important to remember that pretty much it all revolves around the same idea as Bronsted-Lowry, which is it is just one H plus that is transferred. So they do actually come off one at a time. So even though something like sulfuric acid has 2, and a lot of times we look at the overall reaction, like I just wrote here on the screen, as the 2 hydrogens kind of pop off, they actually don't come off both at the same time. They come off one at a time. Same thing with something like the phosphoric acid. They actually come off again here one at a time. So let's take a look at sort of how that sort of progresses. So if we look at something like, say, phosphoric acid, really the first thing that happens is it will actually just lose one H will come off, and that will leave something like H2PO4 minus. The next thing that will happen is actually the H2PO4 minus will then lose one H plus, and we'll leave you with HPO4 2 minus. Again, you can see that as I continue to lose my H plus, I am becoming more negative, right? Every time I lose one, I become one more negative. And the last step that happens is this guy here will lose the final H plus and make phosphate. So this is what is sometimes referred to as a stepwise dissociation of an acid, and it just basically means that they each come off basically one at a time. Would you think it would be easier to remove the first H or the last H? Which one should be easier? It is the first one. The first one is much, much easier to lose because once you do, you then have really something with like a negative charge and you're trying to take away something that's positive. So it's going to hold it a little bit tighter. Gets even harder after you dump off that second hydrogen to remove that third hydrogen. For example, pretty much almost 100% of all the H plus that comes off when this happens is actually just the first hydrogen. There's like very, very small after that. Question? It happens, relatively quickly in a sense. We think about it sort of happen. It's not like they kind of wait. So when that first one goes in, it's going to start producing some of this guy. And if you have enough of that, it's just going to kind of roll off to the next one, and the next sort of process will sort of occur. I don't want to say simultaneously, but it's sort of happening almost at the same time, because some of those things were produced. But there will be a point, and what really happens is, the amount of these guys that you sort of form in that solution is really, really small. It's a very, very small amount. The majority of everything that you got going on is kind of like everything on the very first step is sort of what you have. And that's where a majority of the H plus comes off. So much so that you could almost calculate the pH of the solution just based on the first hydrogen that comes off. Also in 1B, you do a calculation like this, and you find, like, for example, the amount of H plus that comes off, say, in the first step is like 0.1 molar or something like that. The amount that comes off, like in the second step, is like 1 times 10 to the minus 8 or something like that, or to the minus 10 or 13. It's a super small amount that comes off, and even smaller as you kind of get to how much it comes off in sort of that third step. So it sort of all happens at once, and there's not a lot sort of producing on those second steps. Yeah. This is a triprotic acid. This is what is known as a stepwise dissociation, if that's what you're asking. Yeah, so it's a stepwise dissociation of an acid. It basically, it's important to remember that really, although what we look at in this sort of class and most classes is the overall reaction, and we get the overall reaction by just adding all three of these together. And if you do anything that is the same on opposite sides of the arrow would cancel. So like this guy would cancel. This guy would cancel. And what you're left with is a lot of times what we look at in a class like this, which is just the overall reaction of H3PO4 on the left. And we have 1, 2, 3 H pluses that came off. And we're left with phosphate. And that's why sometimes people assume that they all just kind of come off, sort of, at once, but it is sort of a stepwise fashion in which they do come off. And that's also why when we think about Bronsted-Lowry acid conjugate base pairs, these two guys are not pairs, because they are, if you look at the step process here, very far away from each other in terms of what's happening. That is why this guy and this guy are pairs. This guy here and this guy are pairs, and this guy and this guy at the end here are pairs. And again, that's why it's always 1 H plus at a time, because they do come off in a sort of a stepwise fashion. Other questions on that? By the way, phosphoric acid is a weak acid, and there's sort of an equilibrium process that occurs at each of these sort of steps. All right. Now, most acids are oxyacids, and oxyacids are basically guys that contain oxygen and probably one of those polyatomic ions. So if we looked at something like acetic acid, which is this guy, and that is a weak acid, by the way, it looks like this if you draw it. And really, the hydrogen that comes off is this guy right here. So that is the hydrogen that comes off. It is part of, in most oxyacids, like this OH group here. And this OH group is the same thing we talked about with bonding. It is a polar group, which means it's more negative, right? And this guy is more positive, which means there is an unequal sharing of electrons to begin with. And that is why it is able to sort of break this bond relatively easy to allow that hydrogen to come off. By the way, this is also a polar group right here. This guy's more positive. This guy's more negative. So if you think about it, you have electrons kind of moving this way, right? And then there's a positive carbon there as well. That's going to bring the electrons kind of moving in on that bond kind of closer. And that's going to make this bond here kind of weaker and weaker and allow that hydrogen to be the one that's able to sort of be popped off as a result of that. And what I just drew actually is the guy on the bottom as well. That is a carboxyl group, is the carbon, oxygen, OH. And like I said, it's very good for acids because of that polar bond where the electrons are going this way and having that little extra positive guy, again, allowing those guys to really, really weaken. So as we saw in a couple examples, as we've been talking in this chapter, water really could act either as an acid or a base. And as we talked about, things that have the ability to do that are what are referred to as amphoteric substances. And as I mentioned before, besides water, other things that have a hydrogen and a negative charge, I think we did like HCO3 minus the other day. Those are also things that have that ability to kind of go both ways and act as an acid or a base. So in the first one here, we see water acting as an acid, which means it will donate its H plus over. And here, water acting as a base will accept the H plus. Water can even react with itself. One of the waters acts as an acid, one acts as a base, and it's pretty much what is going on in solution or water all the time. You got sort of a reaction of those guys sort of happening. And it will produce some H3O plus, which again is sort of the same thing as H plus and OH minus. And if your water is neutral, you'll have sort of an equal amount of those guys floating around in the solution. And it will be sort of a neutral solution of a pH that's 7 for water, which in reality, if you test water, it's really not 7 in most cases. It's a lot of times more acidic. It's like a pH of 5-ish, 5.4, depending how long your water's been sitting out. So sometimes people are surprised. They like to test water that's been out and it's like not 7. And that's really because if you leave water out, for example, in the air, water will pick up some CO2 and make carbonic acid. And this guy will break apart and increase the H plus concentration in that solution and basically bring the pH down to like 5. So sometimes if you ever need water sort of at a pH of 7, sometimes people will boil water and then use it after they boil it. When you boil water, it makes the CO2 less soluble in the water, liquid part. That removes the CO2 and brings the H plus concentration down a little bit more and bringing the pH back up to 7. So there is a relationship when we talk about water reacting with water, and we do get an equilibrium relationship, which is known as KW. So this is really an equilibrium reaction where we have water basically breaking apart into H plus and OH minus. And when we have a reversible reaction, we could write a K, which is known as an equilibrium constant. And basically an equilibrium constant is products over reactants is how you sort of write that expression. There are two things that you don't include in an equilibrium constant. One of them is a liquid, which is what water is. These guys are aqueous. So that gets us an important relationship, which is known as KW, which is the equilibrium constant for water. It is the concentration of H plus times the concentration of OH minus, and it equals 1 times 10 to the minus 14. Again, when you see the little brackets, that means concentration. And it basically means molarity, which is moles per liter. So we could use this to solve for either the H plus concentration or the OH minus concentration solution if you have one or the other. It's basically the same calculation regardless of which one you're solving for. If you want the H plus concentration, you take 1 times 10 to the minus 14 and divide it by the OH minus concentration. And vice versa, you do the exact same thing. If you want the OH minus, you could take 1 times 10 to the minus 14 divided by the H plus concentration. Really, really, I'll say it one more time, really important in this chapter is to make sure that you do use your exponent button on your calculator correctly. Otherwise, you are going to be wrong on your answers most of the time. So you want to make sure that you punch those things in. As I mentioned before, again, I use H plus, but H3O plus is the same thing. So that's really the acid part. The H plus is sort of the acid part of the solution. The OH minus is like the base part of the solution. And they are related to each other, opposites of each other. As one goes up, the other goes down. So As the concentration of H plus increases, the concentration of OH minus starts to decrease, and obviously vice versa. As the H plus goes down, OH minus goes up. Any questions on that there? Now, can this help us decide? It can help us decide whether or not a solution is acidic, basic, or neutral. So if you do this calculation, again, like we see on the bottom there, and if you find that the H plus concentration is larger than the OH minus concentration, which basically means the acid part of the solution is larger than the basic part, the solution will be acidic. If you do the calculation and the OH minus is greater than the H plus part, that means that basically the base part of the solution is larger than the acid part. It will be basic. And lastly, if you calculate them both to be equal to each other, that means that they will both have a concentration of 1 times 10 to the minus 7 molar. It will be a neutral solution. So technically a neutral solution is at the point where they are exactly equal to each other. And by the way, that corresponds to a pH of 7, basically. Yes. Any questions on that there? All right, let's try some here. Let's make sure our calculators work. For each of the following, all 4 of these different problems, calculate either the H plus or the OH minus and determine is it acidic, basic, or neutral. Make sure to use your exponent button for sure. Okay, let's take a look. So in this situation, you do want to use KW, which by the way, you always have available to you. It is the H plus times the OH minus equals 1 times 10 to the minus 14. And again, for our purposes and most purposes, it always is that number there, 1 times 10 to the minus 14. So really, we're just going to do kind of the same calculation regardless of which one is given to us. In this case, for the first one, we are going to look for the OH minus concentration, which would be 1 times 10 to the minus 14 divided by the H plus, which would be 3.4 times 10 to the minus 4. And if we do that there, making sure we use our exponent button, so 1 exponent button negative 14 divided by 3.4 exponent button negative 4 will give us a 2.9 times 10 to the minus 11. It does need molarity as it is a concentration, so it needs a little unit there associated with it. First off, any questions on the calculation part? So once again, if you were to punch this in your calculator, 1 exponent button, negative button, 14, divide 3.4 exponent button, negative button, and 4 equals, be the way to punch that in. Is this acidic, basic, or neutral, this solution? What we want to do is compare the H plus concentration to the OH minus concentration. Which one is larger? It is the H plus concentration at 10 to the minus 4 is a larger number than 10 to the minus 11. So this solution would be acidic because the H plus is greater than the OH minus. Also important to remember that the negative is important there, right? Because negative 4 means we're going 4 places that way and putting zeros. Negative 11 means we're going 11 places that way and putting zeros. So when you have a negative exponent, the smaller negative number is the larger actual number. Yeah. Any questions on that there? All right, so continuing on, same calculation here for the second one. We're going to be looking for the OH minus, going to be 1 times 10 to the minus 14 divided by 2.6 times 10 to the minus 8, going to get us Looks like 3.8 times 10 to the minus 7 molar. So first guy here was acidic. That would make this one acidic, basic, or neutral. This one would be basic. Again, the OH minus concentration is larger than the H plus concentration that we're comparing it to. Continuing on here, we actually are given the OH minus, doesn't really matter. It's pretty much the same deal. We're going to do H plus in this case is equal to 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. Again, making sure to use our exponent button when we punch that in. It looks like 1.6 to the minus 6 on this one. That would make this one acidic. Again, our H plus concentration at minus 6 is larger than minus 9. You really can just look at the exponents. You don't have to actually look at the front part of the number. And lastly, our last calculation here, same thing. We're going to do our H plus equals 1 times 10 to the minus 14 divided by the OH minus 8.1 times 10 to the minus 3. Going to get us looks like 1.2 to the minus 12, it looks like. That should mean that this guy should be basic based on the OH minus concentration here being larger than the H plus concentration there. Any questions on any of those there? By the way, when you are asked that question, is the solution acidic, basic, or neutral? There is only one answer to that question. It cannot be acidic and basic at the same time. Although sometimes people will give that answer, maybe not for these calculations, but later on, sometimes people will do that. They'll say, hey, it's acidic. And then they'll go, cool, it's basic as well. I never had anybody do all three, acidic, basic, and neutral. So that's good, I suppose. So just one answer for that, acidic or basic when you're asked that, or neutral when you're asked that question. All right, let's try a couple more here. Just make sure, maybe, possibly. All right, so we're not worried about which one's greater. Let's just calculate the OH minus concentration here. And is it acidic, basic, or neutral? This again would be 1 times 10 to the minus 14 divided by 2.8 times 10 to the minus 5. That is going to get us, looks like 3.6 times 10 to the minus 10 molar. That means that it is actually the H plus concentration here at minus 5 that is larger. And obviously it would mean that this guy is going to be an acidic solution in this case. All right. Any questions on KW, how to use it? Yeah. I think it will probably be on the paper. That's a good number to remember, but I think it will show up. Other questions? Now, clear if you're doing any type of homework problem, stuff like that, they sometimes just don't give you that number. You just got to remember, you kind of have that. All right, we'll skip this one, I think. So let's talk about the pH scale. So the pH scale is really the common way that we sort of look at acidity of a solution. And the pH scale does run from 0 to 7 to 14. And if you are below 7, you are acidic. If you are above 7, you are basic. And truly, as we talked about, if the H plus concentration equals the OH minus concentration, it really is 1 times 10 to the minus 7, which means if you are dead on 7, it is neutral. So for our purposes, so there's no misunderstanding, that is what we'll roll with in this class. If it's 7 on the nose, it's neutral. If it's slightly above 7, it's slightly basic. If it's slightly less than 7, it's slightly acidic. So it'll be easy to remember. 7 is sort of your jump off point. If you go closer to 14, you become more basic. If you kind of go towards 0, you become more acidic. So to calculate the pH, this is the formula here. That's not a negative, that's just from PowerPoint. So the pH is equal to minus the log of the H plus concentration. And again, you could also substitute obviously H3O plus in there for H plus as well. Now, if you have this, you want to punch this into your calculator correctly. If you have a display calculator, you pretty much roll exactly the way it is. You want to make sure you hit the negative button, not the subtract. You want to make sure you hit the log button, and then you want to put the number in, obviously using your exponent button. If you have a non-display calculator, you need to, in this formula, pretty much all the other ones, roll backwards. You need to go this way. So you actually need to start with the number, then hit the log button, and then hit the negative button. If you're not sure what type of calculator you got, just hit log. If it says log on your screen, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator, whichever way you go. So, depending on which type of calculator you have, most of them nowadays are display, but there's still some non-display ones, I suppose, as to which way you need to punch it in. You definitely do want to make sure that, again, you use your exponent button when you punch that in. And again, a very common mistake is people want to always use the subtract button. So you make sure it's the negative button when you punch that into your calculator. So let's talk about everybody's favorite thing, which is significant figures. I think we talked about that in this class, maybe. The rule when you calculate something like pH is this: the number of decimal places in the pH value is equal to the number of significant figures in the concentration value. So in this case, we're looking at significant figures to decimal places, not significant figures to significant figures. So significant figures in the concentration. If it has 4 significant figures in the concentration, you should have 4 decimal places in your pH. If it has 1 significant figure in the concentration, you should have 1 decimal place there in your pH. So let's just make sure everybody's calculators work. Calculate the pH here of this solution that has an H plus concentration of 1 times 10 to the minus 5. And do it to the correct number of places. And if you do that, minus the log of 1 times 10 to the minus 5, you should get a 5 staring at you on your calculator, I hope. Again, punching this in, if you have a display calculator, you would hit the negative button, the log button, and then type in 1 exponent button, negative, and 5. Non-display, you would roll 1 exponent button, negative button, 5, then log button, then negative button, and you should be fine. So in this case, we want to give it to the right answer. Should the right answer be 5? Should it be 5.0? 5.00, 5.00000000. Feel like that has a lot of zeros. I'm gonna cross that out. All right, which one should be the right answer here? It is 5.00 should be the right answer. And that is because when we look at the concentration, this guy has 2 significant figures. Again, all the numbers before the times 10 part are significant, which means doesn't give us 2 significant figures, gives us 2 decimal places. So significant figures to decimal places is what we're looking at. Weave through here. Decimal place there. Any question on that? Obviously, this one, by the way, would be acidic, basic, or neutral. It would be acidic is less than 7 in this particular case. By the way, any one that you have basically 1 times 10 to the whatever the pH will always be the exponent if it's just 1 times 10 to whatever it may be. So if you had 1 times 10 to the minus 8, the pH would be 8. Yeah, 1 times 10 to the minus 6, it would be 6, and so forth. Okay, now that we're professionals on that, let us do a couple here. What is the pH of each of these solutions? And while we're at it, is it acidic, basic, or neutral? Okay, let's take a look. So for number 1 here, we are looking for the pH, which is minus the log of the H plus concentration, which they gave us. So we could go right into there, minus the log of 2.1 times 10 to the minus 5. Making sure we punch it in correctly. Use our exponent button. 4.68 here, excuse me, will be the pH of this solution. Any questions on that one? We went with 2 decimal places based off of the sig figs here. 2 gives us 2 decimal places here. Yeah. That is acidic, basic, or neutral. This one would be acidic. Yeah. Again, below 7. Looking at this next one here, number 2. Once again, we're looking for the pH, which is minus the log of the H plus concentration. That is not what is given to us. That is the OH minus concentration. So we do need to get the H plus concentration here. The H plus concentration we could get by doing our KW. 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. And if we do that, gives us like 1.7 times 10 to the minus 7, I believe. Now that we do have the H plus concentration, we could go in and go pH is equal to minus the log 1.7 times 10 to the minus 7. Gets you a pH of 6.77 in this case. The solution would be acidic, basic, or neutral. Yeah, it would be slightly acidic there as well. Now, if you found yourself with a pH of 7.23 on this problem, you did not calculate the pH, by the way, because you used the OH minus concentration, which is not a bad thing. You're just like a slide or two early. So what you calculated was what is known as the POH. If you put that into this equation, which is minus the log of the OH minus concentration. POH uses the OH minus concentration. And if you did that minus the log of 5.9 times 10 to the minus 8 does give you 7.23. That once again is not the pH, but a nice relationship is pH plus the POH equals 14, which means you could then take your POH value, take 14 minus it, 7.23 gives us a pH of 6.77. So all is not lost, and sometimes is a quicker way to do it than maybe using KW. But there's a few different ways you could solve some of these problems, as we'll talk about here in just a bit. But if you did just straight go into the minus the log with that, you actually got the POH, which is actually a scale that runs opposite of the pH scale. And but you can still use it to get yourself to the correct pH. Any questions on that there? All right, we will stop there for now.